we are now going to present the last module, module 3 of chapter 3. In the last two modules, what we did is that we have defined Lebesgue measurable functions and we have developed many properties of these Lebesgue measurable functions. The main thing which we are going to do in this module is that we are going to introduce certain types of functions which are very nice and actually very simple. They are called simple functions, and we are going to see that these simple functions actually form the building block of measurable functions, and they will come very handy when we will ultimately define our integration process, namely Lebesgue integration. We start with the first slide of module 3. The first observation is that the characteristic function chi e of a set E of R is a measurable function if and only if the set E is measurable. Recall what is the definition of a characteristic function. The characteristic function chi e is a function which takes the value 1 at all points of the set E and it takes the value 0 at all points outside the set E. So, it is easy to see that for any real number alpha, if we consider the collection of all x belonging to the domain D, where f x is greater than alpha, where f is chi e, this set becomes either phi or the whole set R or the set D, which is its domain, and consequently we get this result that the characteristic function is measurable if and only if its domain, the set D, is measurable. This also gives us examples of non-measurable functions, because we already know that there are non-measurable subsets of real numbers. So, if E is a non-measurable set of real numbers, then its characteristic function cannot be measurable. A real valued function f defined on a measurable set D subset of R is said to be a simple function if it is measurable and it attains finite number of values on the set D. Suppose f is a simple function defined on a measurable set E, and suppose that f takes the distinct values alpha 1, alpha 2 and alpha k. Then we can write f as sigma I is equal to 1 to k alpha I chi e I, where the set E I is collection of all x belonging to capital X, where f x is equal to alpha I. Observe that since f is measurable, so each set E I is measurable. Further, since alpha 1, alpha 2, alpha k are disjoint, so the sets E I intersection E j is equal to phi if I is not equal to j, that is the sets E1, E2, Ek are pairwise disjoint. And since alpha 1, alpha 2, alpha k are the only values that f can take on the set E, we have E equal to union I is equal to 1 to k E I. This particular representation of a simple function is called the canonical representation of the simple function. So, whenever we will write a simple function later on, we will always consider its canonical representation. Conversely, think that if we are given finite number of measurable subsets E1, E2, En of a measurable set E and finite number of real numbers, say alpha 1, alpha 2, alpha n, and if we consider the linear combination sigma I is equal to 1 to n alpha I chi e I, then it is quite trivial and easy to see that each chi e I being the characteristic function of a measurable set is measurable, and so its linear combination is also measurable, and the resulting function can take at most finite number of values on the whole set E. So, given finite number of measurable sets and finite number of real numbers, also we can construct a simple function. Of course, that particular representation may not be the corresponding canonical representation of that simple function. We now start our first result. Let f be a non-negative bounded measurable function defined on a measurable set E. Then we are going to show that there exists a monotonically increasing sequence of simple functions f n which converges to f uniformly. Before we proceed with the proof, just try to understand that if f and g are two simple functions, then Cf, where C belongs to R, f plus g, f minus g, f g, minimum of f g, maximum of f g, f square, all these functions are also simple functions, and it is quite easy to see, but we will use these facts in the proofs. So, we start the proof, but before that let us define some other notion. For a bounded real valued function f defined on a set X subset of R, we define norm of f as supremum of mod f x, where x runs over capital X. Obviously, norm f is finite if and only if the function is bounded. Now, we start our main proof. We first start with the boundedness of the function. Since the function f has been assumed to be bounded, so norm f is less than infinity. So, let us define a set E as collection of all x belonging to D, where f x is greater or equal to norm f by 2. Again, observe that since f is also assumed to be measurable, so the set E is measurable, and consequently, if we construct the function g1 as norm f by 2 into chi e, then g1 is also not only measurable, but is a simple function, because g1 takes only two values 0 and norm f by 2 on the whole set D. Obviously, 0 less or equal to g1 less or equal to f, and if we consider the function f minus g1, observe that on the set E, the value of g1 is norm f by 2, and the maximum value of f can be norm f by 2. So, the difference cannot exceed norm f by 2, whereas outside the set E, that is on the set D minus E, the value of g1 is 0 and the value of f x is less than norm f by 2. So, in any case, for all points on the set D, the value of the function f minus g1 is always less or equal to norm f by 2, and consequently, norm of f minus g1 is less or equal to norm f by 2. Now, if we consider the function f minus g1, then f minus g1 again have the same properties, that is f minus g1 is again a non-negative bounded measurable function. So, by the first part of the proof, we can find another simple function g2 such that 0 less or equal to g2 less or equal to f minus g1 and norm f minus g1 minus g2, this is less or equal to norm f minus g1 by 2, this is again less or equal to norm f by 2 square. We can just proceed in this way, and proceeding in this way we get a sequence of simple functions gn such that in every step the function gn is a simple function having the property that 0 less or equal to gn less or equal to f minus g1 plus g2 plus gn minus 1 and norm of f minus g1 plus g2 plus gn, this difference is less or equal to norm f by 2 to the power n, and this is true for all n belonging to capital N. Now, note that for a sequence of functions f n, norm f n minus f tending to 0 implies that f n converges to f uniformly, because norm f n minus f is the supremum of mod fnx minus fx, where x runs over capital X. So, in the above observation, choosing Fn as G1 plus G2 plus Gn, we see that since G1, G2, Gn are all simple functions, so G1 plus G2 plus Gn, that is Fn, is also a simple function, and Fn is monotonically increasing because we are taking F1 as G1, then F2 as G1 plus G2, F3 as G1 plus G2 plus G3, where all the functions are non-negative. So, we have a monotonically increasing function of simple functions Fn, which converges to F uniformly. So, we have already proved that if F is a non-negative bounded measurable function, then we can find a monotonically increasing sequence of simple functions Fn, such that Fn converges to F uniformly. Now, we want to extend this result to any arbitrary function which is not necessarily non-negative. So, we want to prove the result for any bounded measurable function. Now, see that any arbitrary function f can be written as f plus minus f minus, where the function f plus is defined as maximum of f and 0, whereas the function f minus is defined as maximum of minus f and 0. So, the functions f plus and f minus are always non-negative, and also observe that f is bounded if and only if both the functions f plus and f minus are bounded, and from the algebra of measurable functions we also can conclude that f is measurable if and only if both f plus and f minus are measurable. This f plus and f minus are called the positive and negative parts of the function f respectively. So, we have now this theorem, theorem 4, that if f is a bounded measurable function defined on a measurable set E, then there exists a sequence of simple functions Fn which converges to f uniformly. Why? Because see that we have already seen that the function f can be written as f plus minus f minus, where both f plus and f minus are non-negative bounded measurable functions. And so, we can apply the theorem 3 to both the functions f plus and f minus, and consequently we can find two sequences of simple functions, say Gn, n belonging to capital N, and Hn, n belonging to capital N, such that Gn converges to f plus and Hn converges to f minus uniformly. Then clearly, if we consider the function Gn minus Hn, then see that Gn, Hn both simple functions implies that Fn is a simple function for each n, and Fn also converges to F plus minus F minus, that is F, uniformly, and so this is our required sequence of simple functions. Finally, we now do away with the notion of boundedness also. So, we start with the arbitrary measurable function. So, let f be a measurable function, any arbitrary measurable function defined on a measurable set E. First, observe that if we define Gn as the function minimum of f and n for all n belonging to capital N, that is what we are doing. So, if f is a smooth curve, then we are actually cutting the curve by a horizontal line at the height of y is equal to n. So, each Gn is bounded, each Gn is non-negative, and since f is measurable and n can be treated as a constant function and so measurable, and we know that minimum of two measurable functions is measurable. So, each Gn becomes measurable and we have Gn is a sequence of non-negative bounded measurable functions, and further Gn converges to f pointwise. Why? Try to understand that if we take any point x from the domain, if f(x) equal to say alpha, then we can always find a positive integer capital N such that capital N is greater than alpha, and consequently every Gn x is equal to alpha for all n greater or equal to capital N, and this shows that the function sequence Gn converges to f pointwise. We are not considering extended real valued functions here, but even if we consider extended real valued functions here, that is if f takes the value infinity at some point, then in that case at that point Gn will take the value n for all n belonging to capital N, which in any case tends to infinity, the value of f(x). So, this assertion is true for any function f irrespective of the fact whether it is a real valued function or an extended real valued function. Now, for each n belonging to capital N, we can consider the function Gn and apply the result theorem 4 to the function Gn. So, by theorem 4, I have for each n belonging to capital N, there is a sequence of simple functions which is converging uniformly to Gn, and from this sequence of simple functions we can choose a particular simple function, say fn, such that 0 less or equal to fn less or equal to gn, and norm gn minus fn is less than 1 by 2 to the power n, since the convergence is uniform. Finally, observe that for all x belonging to E, if we consider modulus fx minus fnx, this is less or equal to mod fx minus gnx plus mod gnx minus fnx. This is less than mod fx minus gnx plus 1 by 2 to the power n, since we have already seen that norm gn minus fn is less than 1 by 2 to the power n. And if we look at the right hand side, 1 by 2 to the power n tends to 0 as n tends to infinity, and mod gnx minus fx also tends to 0 as n tends to infinity, and consequently we have mod fx minus fnx tends to 0 as n tends to infinity. So, I have a sequence of simple functions fn which is converging to f pointwise, and so we have this final result that if f is a measurable function defined on a measurable set E, then there exists a sequence of simple functions fn such that fn converges to f pointwise. Let us summarize what we did in the last module, module 3 of chapter 3. We have defined a special type of measurable functions which are called simple functions, and if you look at the canonical representation of simple functions, you can now understand that the notion comes from the notion of step functions. Actually, step functions are functions which takes finite number of values on an interval. So, in other words, the interval, closed interval a b say, is divided into finite number of sub intervals, and in each sub interval the step function takes a constant value. Now, instead of sub intervals, if we take measurable subsets, then we get the notion of simple functions. So, simple functions are nothing but more general form of step functions, where we are using measurable sets instead of intervals. And we have seen that for any measurable function f, we can find a sequence of simple functions which converges to the measurable function pointwise. If the measurable function is bounded, then we can choose the sequence of simple functions in such a way that the convergence is uniform, and moreover, if the measurable function is also non-negative, then we can actually choose the sequence of simple functions such a way so that the sequence is monotonically increasing. And with this we finish this module.